Hey everybody, welcome to another LeetCode video. Today we're going to solve LeetCode 173, BST Iterator. So every time I solve a BST question, I try to give a quick overview of what a BST is. Please let me know if that's a waste of time. But yeah, so a BST is a type of binary tree where for every node, the value of the left children are smaller than the node's value, and the value of the right children are either greater than or equal to the node's value. However, some computer scientists may define a BST where the left children are smaller or equal, and then the right children are strictly larger. So watch out for that. And if you encounter a BST question in an interview, best thing to do is to ask your interviewer to clarify whether the equal nodes should be on the left side or on the right side. Don't just assume. So this question wants us to design a BST iterator class that iterates through a BST in ascending order of the value of the nodes and also writes a function to see if the iterator has next value. For example, the ascending order of this BST is this guy. That's the ascending order, so it goes from like 2, 4, 5, 6, 8, 10, and 12, which also happens to be the in-order traversal. So in binary search trees, an in-order traversal goes through the nodes in ascending sorted order. So that's one approach we could take. We could iterate through the tree in an in-order fashion and add all the nodes to a list and then use the list as a reference for the iterator class. However, we would be using extra space because we'd have to store a list of the in-order traversal of the nodes. Now, I just want to say that it's no shame if you take this approach in an interview, as long as you can discuss like the trade-offs and maybe talk through an optimal solution, you'll be fine. So there's a better solution, of course, that doesn't involve storing all the nodes in sorted order, and that's a brilliant one actually. We're going to maintain a stack of the smallest element in the BST, and every time we pop a value out of the stack, we update the invariant of the stack. So that means that the top element of the stack would always have to be the smallest element in the BST. So every time we'd call the iterator.next function, we would get access to the smallest value in the BST. So what do I mean by that? Say for instance, this is our stack, so it would be something like this. And then just assume for now that we have the values 2, 4, and 5 in the stack. When we pop 2 out of the stack, say for example we pop 2 out, the next smallest value in the stack would be 4. That's this guy. So when we pop 4 out of the stack, the next smallest value would be 5. That's 5. So that's it. That's like a simple example. So now let's run through like an actual example using this binary tree that we have and see how the solution works. So first we're going to add all the values in the leftmost branch of the BST. So the smallest value would be at the leftmost branch of the root node. So the leftmost value is 2, and 2 just happens to be the smallest value. So in a BST, the smallest value would be the leftmost child of the root node. So leftmost child of the root node is 2, that would be the smallest value. So we're going to add all the values in the leftmost branch of the BST. So that would mean that we would add 6 to the stack, and then we add 4, and then we add 2. That's all we have to do for now. So now that we have this stack, whenever we pop the top value, which should be the smallest element, we have to update the state of the stack. So for now, we can pop 2 out because 2 is the smallest value in the stack. So if we implement like an iterator class, we can just pop 2 out as the smallest value, which is fine. But after popping 2 out, we'd have to update the invariant of the stack, meaning we need to have the smallest value at the top of the stack. Just have to maintain the state. Now, whenever we pop up an element out, we can be in two positions. Either the node we just popped out doesn't have a right child. In that case, everything's good. We do nothing. But if the node we just popped out has a right child, that right child should be the next smallest value in the BST, so we should add it to the top of the stack. So for instance, let's say we're implementing the iterator class. We pop 2 out, which is fine. So whenever we pop an element out, we ask, does it have a right child? No, 2 doesn't have a right child, so that's fine. So we pop 2 out. And then let's say we call the iterator.next function method, and then we pop 4 out. So in popping 4 out, we have to ask ourselves, does 4 have a right child? Now, if 4 has a right child, which of course it does, in this case, when we've popped 4 out, the next smallest value in the BST is not 6. The next smallest value is 5. It's the right node of right child of 4. So what we do is whenever we pop an element out that has a right child, we just call the function to add all the values in the leftmost branch of the right child. So for now, the leftmost branch of the right child only has one value, which is 5. Say, for example, if there was something else here, then we'll just add the left branch of the right child, because we know that the left branch of the right child should be smaller than whatever is on top of the current node that we're looking at. So 5 is smaller than 6, so we'd have to add 5 to the stack. So in this case, we'll just add 5 since it's the only node in the leftmost branch of the right child. So we add 5. 5 is now the smallest element in the BST. Say for instance we pop 5 out. So let's say we pop 5 out. And then after popping 5 out, does 5 have a right child? No, it doesn't have a right child, so that's fine, everything's okay. And then, which means the next value in the stack is in its rightful order. 6 is the next smallest value in the stack. So let's say we pop 6 out, and if we pop 6 out of the stack, does 6 have a right child? Yes, 6 does have a right child. So after popping 6 out, we add its right child, the leftmost branch of its right child, we add it to the stack, so that would mean it would be this guy. So we would add 10 and 8 to the stack, so 10 and 8, and then we pop 8 out, take 8 out. Does 8 have a right child? No, it doesn't. That's fine, we leave it. And then we get to 10, we pop 10 out. Does 10 have a right child? Yes, it does. So after popping 10 out, we have to add the leftmost branch of the right child of 10. So that would mean it would be this guy. And 12 is the only value there, so we add 12 to the stack. And then when we call the iterator.next class, we'll just pop the top of the stack, that would be 12. So popping 12 out would just take 12. And then the values that we return in the order would be 2, 4, 5, 6, 8, 10, 12, which is the same as 2, 4, 5, 6, 8, 10, and 12. So that's how you implement it. Like the only two things you have to keep track of is that whenever you pop an element out of the stack, you have to maintain the state of the invariant. You have to maintain the state of the stack, which means the smallest element should be at the top of the stack. So if an element has a right child, you know that the right children, like the leftmost node of the leftmost branch of the right children, should be smaller. So you add it to the top of the stack, and then you continue doing that for the iterator. It's going to be clear as we go through the code, so let's do that. Also, we have to implement like a function that checks if there's like a next value for the iterator to go through that has next. So the way we implement that is fairly simple. We just like check the size of the stack. If the stack has elements in it, then we know there's a next value to check. If there are no elements in the stack, then there's no elements to check. So that's how you do that. So let's talk about like the time and space complexity of this algorithm. So for time complexity, we're doing two main things. First, we're adding stuff to the stack, which takes O of 1 time. And the main expensive operation that we're doing is that when we're adding the leftmost branch of the right child, or like the leftmost branch of the root node, that is like an expensive operation, but we only do it when we do have like, when the thing that we pop out, when the element that we popped out does have a right child. If it doesn't have a right child, we don't do anything. So, I mean, if it has a right child and then we add the leftmost branch of the right child, that would be an O of n operation. And then when it doesn't have a right child, we just don't do anything. It's like an O of 1 operation. So if you're familiar with like the concept of amortized time, which means that if you're doing one specific kind of operation more times than the other, then that kind of like takes precedence in big O notation. So for time complexity, that would be O of 1 technically because of like amortized time. And for space complexity, we're storing, potentially we could store all the nodes in the BST. So where n is the number of nodes, so space complexity is O of n. So yeah, that's how you solve this question, guys. Let's dive into the code. So the code's going to be surprisingly very simple. The first thing we're going to do is make a stack of tree node. I'm just going to call it stack. And then we can just like initialize the stack in the constructor here. So we can just set this dot stack. That would be equal to new stack and tree node, right? And then when we're like building this next method, we'd have to add the leftmost nodes of the right child, or the leftmost nodes of the root node. So let's make a function. Let's call it public void add leftmost. So what this is going to do is it's just going to add the leftmost child, leftmost branch of any node that we pass to it. So whether it's the root node or like the right child of a particular node, it's just going to add like the leftmost branch of that. So this while node is not equal to null, we just like stack.push node, and then we can just set node is equal to node.left. So fair enough. And then we can just build the next method. So we pop something out of the stack. So tree node top would just be like stack.pop, and then we have to do two things. Like if the top.right, like if it has a right child, if it's not equal to null, then it has a right child. So if it does have a right child, we just like add the leftmost branch to the stack. And then if it doesn't have a right child, we can just like return top. And also if it does have a right child, after adding the leftmost branch to the stack, then we can return it. So that's it. Let's not forget to add the leftmost branch of the root node when we initialize the BST Iterator class. So just let's call add leftmost and root. And that should do it actually. Oh wait, we still have to implement this function. So for this function, simple thing is return stack.size. If it's greater than 0, then it has next. And that's it. Let's run this and see what happens. Return top.value, I think. Yeah, top.val. Let's run this. Awesome. It's accepted. So yeah, the code's very short. I mean, for like the very lengthy explanation that I did. So let's submit this. And it's successful. So yeah, that's how you solve this question, guys. I'm going to include the in-order traversal method in the code that I'll be uploading to GitHub, so check it out. And if you like this type of content, please consider subscribing to the channel. Comment down below if you've got something to say. Don't forget to share this video around the community. I'm trying to upload a few more videos, so it would be good if you share it to people that this might help. I'll see you in the next one. Bye.